The last video showed some promise for a fin testing system, but raised a number of questions, especially about repeatability. The objective is to try and come up with a way to compare fins side by side and how various changes you can make to a fin affects their performance. Drag, lift, when a fin spins out, and what makes a fin head upwind well are all things I'd like to measure. A cheaper, faster way to test out new fin and board concepts is also an aim of this project. Firstly, I needed a way to quickly change fins, so I designed a half-scale tuttle system that uses magnets to hold the fin in place. The magnets have their poles swapped, so you can't put a fin in backwards. This will make more sense for annular or symmetrical fin testing in future. I designed and 3D printed a number of fins. Each of them I wrote some hieroglyphics on the side, which may require some explaining. NACA stands for National Advisory Committee for Aeronautics, which standardizes airfoil shapes. I'm using a basic 4-digit airfoil, which always has the maximum width at a position of 30% of chord length. The last 2 digits are the maximum width of the foil divided by the chord length in percentage. So a 9mm wide foil with a chord length of 100mm is called an NACA 0009. I will call this from now on a NACA 9. The shape is mathematically defined. The first 2 digits define the camber, which is irrelevant to this experiment at present, so is always 00, which means the airfoils are like a strut and what the majority of fins in the real world look like. A guy in Melbourne has made a nice online database called airfoils.com where you can download a large selection of NACA airfoils. He also made a free plugin for Fusion 360, which is how I designed all these fins. I draw a NACA 9 on the base of the tuttle connector, then another smaller NACA 9 at a place I want the tip of the fin. I draw a line defining the leading edge and trailing edge of the fin, and then I use the loft command to join the two airfoils. I use guide rails to follow the leading edge and trailing edge. The other number scribbled on these fins is the layer height I printed these fins with on my 3D printer. My printer can print as fine as 0.05mm to a maximum of 0.3mm layer height. The idea was a fin with 0.3mm layer height would simulate a very rough surface fin. The 0.05mm printed fins I also sanded as smooth as I could. I tried to print a selection of fins with only one change between them, for example, just adding a bulb for any particular surface finish. It takes about 10 hours to print a smooth fin and about 1.5 hours to print a rough fin. I made a jig with identical magnetic tuttle system to spin the various fins around at a fixed angle of attack. I again designed this in Fusion 360. It used holes to index the angle of attack so I could repeat for various fins. I defined a 0 angle of attack as the angle which made the fin travel exactly tangentially around the spin axis. Because this is behind the spin arm, it's slightly not perpendicular. I added one hole at a negative angle of 2 degrees, and the rest of the holes were placed at 2-degree increments up to 20 degrees. To test my construction work, Fusion 360 allows you to import a picture of your creation and measure the angles or other measurements. This way I had a correction table which may become important for lift calculations later. However, the main thing is the angle of attack can be repeated for various fins. To measure speed, I initially tried using Jan Hainen's DIY GPS, but above about 10 km per hour the GPS got confused and output garbage. Spinning on a single arm with a GPS and a GoPro at high speed, the system started oscillating badly and dangerously, and the system couldn't travel around the pool at the same height, so I needed to make a counterbalance system. Before doing that, I spun the initial board system around with the various fins. However, I had made these fins larger than the original fin, so I could not make the system spin out. The board would more likely fly out of the water due to centrifugal force. There didn't seem to be much difference between the fins until I tried a NACA 24. This was a much fatter airfoil shape, roughly like a fangy fin, and since it was much bigger, I only printed at 0.3mm layer height. To my surprise, this allowed the board to travel much faster around the pool before the board would lose control. It would lose control about 5.3 meters a second compared with around 4.4 meters per second for all the other fins. This is a 20% improvement in speed. However, it took a lot more current to spin at this speed. Since I could not reproduce the original spin-out effect with these larger fins, I designed and printed another set of fins with the same magnetic tuttle system that were as close to the original fin size I'd used. Since it appeared the fatter NACA 24 airfoil showed a large improvement in some ways, I included some smooth and bold versions as well as the NACA 09. Whilst those smaller fins were printing, I got the counterbalance system made. One side I can add various weights to roughly compensate for the mass of whatever it is attached to the other side. I used a bike computer to measure speed, but had to print a magnet ring which had 6 magnets to allow the bigger circumference of 3.2 meters. It appeared this allowed me to measure the speed fairly accurately down to 3 kilometers an hour, up to the maximum the system was capable of 40 kilometers an hour with my current power supply. Since this video is already quite long, I'll stop here and continue on the next. If you like this kind of content, please subscribe, mash that like button, make some comments. Whilst I'm doing these experiments regardless, making these videos takes time, and you guys interacting with the videos will motivate me to keep posting them. Any kind of feedback is good, so let me know if there's stuff you want to see more or less of. Thank you.